Hi there, this video is on graphing polar equations. So in the previous lesson, we had introduced the polar coordinate system and talked about plotting points in the polar coordinate system and how polar coordinates are in the form r comma theta, where theta is the independent variable and r is the dependent variable. And then we had started looking at some polar equations, and we had talked about going back and forth between polar form of the equation and rectangular form of the equation. And we saw that one example in particular of the cardioid, where the rectangular form of the equation was super complicated, and trying to graph from that would be really difficult. But using what we know, in this lesson, we're going to be looking at graphing polar equations. And we're going to start really simple. So this first one, r equals to 3. So that means for all values of theta, r will be equal to 3. So you can almost think about like starting at 0, and then rotating around passing through the infinitely many angles. R will always end up being equal to 3 and therefore make a circle that is centered at the origin. And this circle has a radius of 3. And then to go to rectangular form of the equation, you could either replace the r with the square root of x squared plus y squared, or you can think about squaring both sides so that there's r squared equals to 9. And then r squared is able to be replaced with x squared plus y squared. And now we have the equation of a circle in rectangular form, and this is something that we're more familiar with. So we have our circle with center at, well, in the xy plane, it would be 0, 0, and then we could also describe the pole at r comma theta as being 0, 0 as well. And radius equal to 3. Okay, so r equals to a constant. That's going to be a circle that's centered at the origin. And then we also talked about in the last lesson, theta equals to an angle. Okay, so theta equals to negative 5 pi over 6. We go, okay, well, where is negative 5 pi over 6? Where does that terminate? And negative 5 pi over 6 terminates, here, let me use this. So negative 5 pi over 6 terminates where 7 pi over 6 terminates, okay? And if we think about this equation, for all values of r, theta will be equal to negative 5 pi over 6. So if r is positive, we're going in this direction, graphing points. Here, I'll use the color now. Towards the terminating side of the angle. And then if r is negative, we're going away in the opposite direction, towards pi over 6. So this ends up graphing a line. And if we take theta equals to negative 5 pi over 6 and think about taking tangent of each side of the equation, which you could technically think about taking sine or cosine. It's just then you're going to have more work. It's most efficient to, because we're trying to go to rectangular form. So you're trying to eliminate all the r's, all the thetas. So it's the most efficient to think about taking the tangent of each side of the equation, because tangent of theta is equal to the ratio y over x, whereas like sine of theta would be y over r. We'd have to think about eliminating the r then. So it's most efficient to just think about taking tangent and then replacing. See, I'm mixing myself up. So taking tangent of both sides of the equation and replacing tan theta with y over x. And then we think, okay, tangent of negative 5 pi over 6, that's going to be root 3 over 3. Okay, so we get y equals to root 3 over 3 times x, which represents a line with a slope equal to, having issues with writing right now, with a slope equal to root 3 over 3, positive root 3 over 3. So these are some of the common polar curves that we're going to explore. So we're next going to be checking out circles that are not centered at the origin, but are either just to the right of the origin, to the left of the origin, above or below. Sorry, I keep saying origin. I mean the pole, because we're in the polar coordinate system. So like if sine is in the equation, so r equals a times sine theta, then that's going to be a circle that is symmetric about the vertical axis, whereas r equals to a times cosine theta will be a circle that's symmetric about the polar axis. Okay, and then we'll check out some of the limestone family, the roses, and lemniscates. Okay, so we're going to use what we already know to help us with graphing these polar curves, okay? So r equals to 3 times cosine of theta. We're like, hey, we need to determine different values of r depending on what values of theta we choose. Well, we know how to graph in the xy plane y equals to 3 times cosine of x, right? And so then we can think about, okay, well, for different angles, what would the value of r be? R would end up matching the same values as the values of y for the graph of y equals 3 times cosine of x. So that's cosine vertically stretched by a factor of 3. So I can scale the x-axis by pi over 2s. Okay, up to 3, down to negative 3. Cosine starts high. So plotting kind of those feature points, the high and low points and the points that intersect the x-axis and are also on the midline of the graph. Okay, so referencing that graph in order to plot points, notice if we start picking just those points that we plotted on the graph of y equals to 3 times cosine of x, watch what happens. So like for 0, notice 0, 3 is a point. So thinking about, okay, well, that means that when theta is equal to 0, r would end up being equal to 3. So here's our point. And then if we go to the next point we have plotted, so pi over 2 comma 0, then we're thinking, okay, well, for pi over 2, r is equal to 0. So we're at the pole. And then if we go down to this lowest point here, pi comma negative 3, well, that means whenever theta is equal to pi, r would be equal to negative 3. So that's actually just back at this original point. And this will keep happening if we just keep choosing, in this case, the points that we have plotted here. So we do want to think about finding some extra points. So like thinking about pi over 4, and then that would be 3 root 2 over 2, which is approximately 2.121, which is to help with graphing. So then coming over here, I can say, okay, when theta is pi over 4, r, I'm counting out approximately 2.121, so just past where r is equal to 2. Okay, and then we could do 3 pi over 4, and then comma negative 3 root 2 over 2. So negative 2.121. So going over to 3 pi over 4, since r is negative, that means we're counting in the opposite direction. So we have 4 points. And I just know some students ask me, like, oh, is it a square? Well, no, like we could keep finding additional points. Like we could think about if we were to plug in pi over 6, right? So like if we had plugged in pi over 6, we would have gotten 3 root 3 over 2. And if we keep choosing, so like pi over 2, if we'd done like 2 pi over 3, right, then we could have gotten, was that negative 3 halves, and so on. So like negative 3 halves for 2 pi over 3, we'd have to go in the negative direction down to, what, about there. But what we end up with is a circle that is not centered at the pole. It's actually centered at 3 halves, comma 0, right? Thinking r comma theta. And this circle has a radius equal to 3 halves and a diameter equal to 3. So if we look at our equation, we're like, hey, 3, 3. Okay, and then, oh, the radius is half the diameter, and that corresponds to the center here. So if you want to try and generalize, you can go through here and think about like where the center and what the radius would be for each of these equations. So you can pause and like take a moment to do that if you'd like. But all of the cosine graphs, the like a number times cosine theta, will end up being symmetric about the polar axis. So it's just the circle would be to the right of the pole, or it would be to the left of the pole, and touching the touching the pole. I keep mixing up my terms here. And it's kind of cool because if you were to think about like adding or subtracting an angle to theta, like trying to apply a transformation, then it's going to end up kind of rotating the circle in whatever direction it is. So like if you're adding pi over 4, it's actually going to be rotating in the negative pi over 4 direction, or like subtracting pi over 4, it would be rotating in the pi over 4 direction. Okay, so similar equation, but with sign. So let's check out what happens. So similar strategy for graphing. Let's think about the graph of y equals to 3 times sine of x in the xy plane and use that as a reference. Okay, so we can again scale by pi over 2. So using what we already know to help us with graphing these polar equations. Let's use another color. Okay, so sine passes through the origin, goes high, then comes down low. And this is just a rough sketch for me to use as a reference here. So I can see like 0, 0. Lies on the graph of y equals to 3 sine x. Well, 0, 0, r equal to 0, whenever theta is 0, will just be the pole. Okay, and then we know we had to find an extra point. So like pi over 4, and it would again be 3 root 2 over 2, which was approximately 2.121. So just past r equals to 2. And then coming back over to the graph. So looking at the point pi over 2, comma 3, that means whenever theta is pi over 2, r will be positive 3. So counting 3 rings out. And then 3 pi over 4 would also be 3 root 2 over 2. So here we are. Okay. And then at pi, we're back to 0. And you could think about plotting some additional points to check out the shape. This is what happens. Okay. So we can see here, like if we think about it, 0 to pi over 2 is Q1. So Q1 makes this part of the circle. And then pi over 2 to pi, so Q2 makes this part of the circle. And if we reference the picture above, it was also only an interval of pi that we needed. So from 0 to pi over 2, our values were positive, so that made this part of the circle. And then from pi over 2 to pi, our values were negative. It makes sense that these values are in what we would think of as quadrant 4. Or those points are where we would think it being quadrant 4 for those Q2 angles. So thinking about what we can generalize about these equations, well, all of their graphs are circles, right? They're circles with a radius based on how these equations are written. The radius is A, and the diameter is 2A. So for whenever the equation is cosine, the center of the circle would be at A comma 0, and the circle would be symmetric about the polar axis. Okay, or the horizontal axis. And for sine, the center would be at A comma pi over 2, with the graph being symmetric about the vertical axis, or theta equals to pi over 2. Now, whenever A is positive, the graph, so for like r equals to 2a cosine theta, the graph would be to the right of the pole. And whenever r is equal to 2a times sine theta, and a is positive, the circle will be above the pole. And then whenever a is less than 0, the circle will be to the left. And the sine equation, when a is less than 0, will have the circle below the pole. Okay, so you should get to the point where you recognize that this equation represents a circle. And a circle that is either to the right of the pole, to the left of the pole, above the pole, below the pole. you should get to the point where you can recognize that. And there's a little summary of what we talked about for circles. Okay, so now we are entering the limacon family. Okay, and there's different types of limacons we're going to talk about. So cardioids, we already checked out a graph of a cardioid when we were converting to a rectangular form of the equation of a cardioid. It might have even been this one. But we're going to use the same strategy that we did for graphing the circles. Let's think about using the graph of y equals to 2 plus 2 cosine theta as a reference for, y equals to 2 plus 2 cosine of x in the xy plane to use as a reference for determining values of r that go with different angles theta. So nothing's happening to the period. We can scale our x-axis by pi over 2's. Now the plus 2, that means our midline is at 2. And the amplitude is 2. Okay, so the graph, start high because it's cosine. It might be helpful if I draw the midline. Then come down and finish high. Okay, so let's plot those points and see what we end up with. And this is a cardioid. We talked about cardioids before. They end up making like kind of heart-shaped curves. Okay, so referencing this, whenever theta is 0, r will be 4. 1, 2, 3, 4. Okay, whenever theta is pi over 2, r will be 2. I'm looking at this point here, it's on the midline. So it's pi over 2, 2, 1, 2. Okay. And then when theta is pi, r is 0. Okay. And then for 3 pi over 2, r is 2. 1, 2. Okay, notice no negative values for r based on this graph. And then for 2 pi, we're back to 4. Now, it's kind of hard to tell what's happening here. You do want to get to the point where you recognize that this equation does represent a cardioid. And here's the thing. So just touches the x-axis, right? Just ends up touching, like make the pole. And if notice that between like 0 and pi over 2, so those quadrant 1 angles, right, between 0 and pi over 2, those are values that are between 2 and 4 for r, okay? So, and then between pi over 2 and pi, those would be values that are between 0 and 2, so smaller values of r. And then again, smaller values of r between pi and 3 pi over 2, and then the larger value, so between 2 and 4 for quadrant 4, 3 pi over 2 to 2 pi. So what ends up happening, this is a very rough sketch, is something like this, where it comes and it touches. You could find additional points if you want, but you just have to have the general idea of what the graph looks like. And we make that kind of heart shape. Okay, so next we're going to check out a limacon that has an inner loop. And I think that after we graph y equals to 2 plus 4 cosine of x in the xy plane, it'll make sense why that is. So there's a vertical shift up 2, and the amplitude of this cosine curve is 4. So again, scaling by pi over 2's. Okay, and then that means that this will be 6, 2, negative 2. Okay, cosine, and this is in the xy plane. I should label the midline here. Okay, but starts high and then comes down low, back to the midline and finishes high. Okay. And it would be probably helpful for us to figure out what these points are in this case. You don't always have to do that, but just for this first graph, and like after you get to the point where you recognize like, oh, this is a limestone that has an inner loop, you don't really have to do this. But if we were to think about setting r equal to 0, or if you want to think about the equation in the xy plane, right? So setting y equal to 0 here, we'll think about it that way. Okay, so that ends up being cosine theta, or cosine x, I'll just leave it as theta, equals to negative 1/2. So when theta is equal to, let's just think about from 0 to 2 pi. So 2 pi over 3 or 4 pi over 3. So this point would be 2 pi over 3. This would be 4 pi over 3 is whenever r would be 0. So we'll get back to that in a second. Whenever theta is 0, r will be 6. So we actually come just off of, don't have enough rings on here. And then at pi over 2, be it r is 2. Okay, and then we can use the fact that 2 pi over 3, r would be 0. Okay, so right now the graph is kind of coming around here. It was positive before, r was positive before it hit 2 pi over 3. So it would kind of come up here. Okay, and then, okay, at pi, r would be negative 2. So that means we're going 2 rings towards 0. Okay, and then to the left of pi though, so the angles that are before pi, r was also negative. So what's happening is this loop is created. And then when we look at the angles to the right of pi, between pi and 4 pi over 3, okay, we are getting negative values of r again. Okay, so the loop kind of comes around. And then at 4 pi over 3, we're back at r equals to 0. And then 3 pi over 2, r is 2. And we can see that from 4 pi over 3 to 3 pi over 2, the r values are positive. And then, where are we? And then at 2 pi, we're back at 6, so it's going to come back around here. That's maybe a little bit stretched out. I feel like it's probably a rounder graph. Here, let's go ahead and check this out in Desmos, just to make sure we're close. So if we have r equals 2 plus 4 cosine theta. There we go. Oh yeah, it should have been rounder. My graph is too stretched. It's too stretched looking. Here, let's try this again. Okay, make it a little rounder. And again, you could always plot more points. Mine's still kind of stretched out looking. Okay, but there's that inner loop, and that loop happens because of this dip here in the graph below the x-axis that causes those values of r to be negative. So that's what causes the loop, the inner loop. So summary of limesons so far. So cardioids are whenever these two values are the same, right? Whether sine or cosine, the sine or cosine will determine the orientation or the symmetry, like where the graph has symmetry. So if those values are the same, just like this equation, 2 and 2, it'll be a cardioid. But it's in the case that B is greater than A, so let me use a different color here, that B is greater than A, or at least the magnitude of B is greater than A, where the graph of cosine, like in the xy plane, we would think of that as the graph would end up, the shift is less than what the amplitude is, so the graph dips below the x-axis, and that's what causes the loop for either the sine or the cosine equation. Okay, and you can see these rules for the loops. It's not something you have to pay too much attention to, especially if you're using our method of graphing and referencing the graph of the sine or cosine equation in the xy plane. So the values of theta for which r is equal to 0 are called polar zeros of the function r equals to f of theta, and that should make sense, right? So whenever r is equal to 0, and the point would be at the pole. So in the above form, when the absolute value of A is greater than the absolute value of B, so that means that if we're thinking about the sine or cosine equation, that means the vertical shift is greater in magnitude than the amplitude. So in that case, those graphs would have no x-intercepts. Like they would be either completely above the x-axis or completely below the x-axis in the xy plane. And that translates to then the graphs having in the polar coordinate system, these graphs not having any polar zeros. So the graph will either resemble a circle that's kind of like flattened at one side, or it'll be look like a kind of having like a dimple that doesn't touch the pole. Here, let me go back up here. So a dimpled limason would be like so, where you can see there's just this little dimple. This picture doesn't do a great job, but it's meant to show in the case that A is greater than or equal to 2B, that there's a flattened side. Like let's say that this side is maybe a little bit more flattened. And we'll see that because I actually have a typo here. And this next graph, I believe, is actually a convex limason. Here, I can fix this. A convex limason. So it'll just kind of have a flattened side. And that's because 4 is greater than or equal to 2 times 2. Okay, if you saw that above, what we were just looking at, right? If A is greater than or equal to 2 times B. So not just A greater than B, if A is greater than or equal to 2 times B, then this convex limacon occurs. Okay, so same strategy for graphing. Let's think about graphing y equals to 4 plus 2 cosine of x in the xy plane. So the vertical shift is 4, but the amplitude of the waves, the sinusoidal waves, right, are 2. Oops. So 2, 4, 6. Okay, this is cosine, so we again start high, pass through the midline, go low, finish high. Oops, my graph's a little off, but that's okay. Maybe it's not okay. Here, we'll fix it. Oof. Okay, that's a little better. Okay, so whenever r is equal to 0, whenever theta is equal to 0, r will be 6. Okay, and then at pi over 2, r is equal to 4. 1, 2, 3, 4. Notice these are all positive r values. And for pi, r would be 2. And you could imagine if it were a vertical shift down where the entire graph was negative, then all the r values would be negative. And 3 pi over 2 corresponds to r being equal to 4 again. 1, 2, 3, 4. And 2 pi is back to r being 6. So this graph kind of comes around and then it like flattens out. It almost reminds me of like a guitar pick. But it looks something like that. You can check it out on Desmos. Okay, so now we're getting into my favorite, the rose curves, just because they're fun. Although they remind me more of like daisies than roses. But kind of same strategy as before. Let's think about graphing y equals to 3 times cosine of 2x. So that means that the period would be pi, horizontal compression by a factor of 2. But I'm going to still graph to 2 pi. So here we go. Pi over 2, pi, 3 pi over 2, 2 pi, and then 3, negative 3. Oops. Oh, that's right. That was silly. I forgot what I wanted to scale. Okay, if the period is now pi, because we've horizontally shrunk by a factor of 2, that means that the period is pi, so I want to scale by pi over 4s. There we go, that's better. Okay. So again, this is thinking about graphing y equals 3 times cosine of 2x in the xy plane. So we can use this graph as a reference for determining values of r for different angles theta. So at 0, when theta is 0, r is 3. 1, 2, 3. Here we go. And then at pi over 4, r is 0. But notice how between 0 and pi over 4, r is positive. So all those angles, r is positive. Okay, and trending down towards 0. So it looks kind of like that. Okay, and then, so here I'm going to highlight this part of the graph. And then we go to pi over 2, and we're at negative 3, so that means we're counting 1, 2, 3 towards 3 pi over 2. But also notice that that means that between pi over 4 and pi over 2, our values were negative. So the graph would have gone like kind of like so. Okay, and then r is still negative between pi over 2 and 3 pi over 4. Okay, so that means that would be this part of the graph. Use another color to highlight. Okay, and then between 3 pi over 4 and pi, r is positive again, and we're going up to 3 at pi. 1, 2, 3. R is positive between 3 pi over 4 and pi, so like that. Do blue. Kind of tedious. Okay, R is still positive between pi and 5 pi over 4, and then at 5 pi over 4, R goes back to 0. Sorry, that was that part of the graph. So between pi and 5 pi over 4, okay. And then we keep going in. So once we start repeating, like retracing over the graph, that we know that we're done. So we're not quite done yet, because now as we go from 5 pi over 4 to 3 pi over 2, we have negative values of r. And then at 3 pi over 2, we can see we're at negative 3, which means we end up counting 3 towards pi over 2. Okay, so that would that part of the graph. And then still negative between 3 pi over 2 and 7 pi over 4. So that ends up being this part of that looked kind of similar, but that's okay. And then from 7 pi over 4 to 2 pi, r is positive, and we finish back where r is 3. So we have created our rows, okay, referencing the graph of y equals 3 times cosine of 2x in the xy plane. Okay, so there were 4 petals. This is a rose curve. There are 4 petals. And also notice how this first petal is on the polar axis here, and this is a cosine equation. Go ahead and use your calculators and do your own exploration of seeing how many petals each of these equations has. So let's do one where we're still going to do cosine, but let's do this equation and see what happens. So now theta is being multiplied by a different value. Okay, and you can even pause this video and try this on your own first if you want. I'm going to go through this one kind of quickly. The period would be 2 pi over 3 when we divide by 4. That means that if we have 2 pi over 3 and then we divide by 4, that's the same thing as multiplying by 1/4. Oh, that would be pi over 6. So we're going to scale our x-axis by pi over 6. 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6. So 2 pi over 3 is 1 period. I think we have to go a little bit further. How about let's go to pi and see what happens. Again, you know you're done once the graph starts like repeating itself. So 4, -4. Okay, thinking about cosine. Okay, the graph continues on. Okay, so referencing this, here's 0, we're out at 4, 1, 2, 3, 4 for R. Positive, positive, positive to pi over 6 and then hit 0. Okay, between pi over 6 and pi over 3, R is negative. R is negative, so between pi over 6 and pi over 3, R is negative. Okay, and at pi over 3, R would be out here, 1, 2, 3, 4. Sorry, -4. Okay, so thinking about where those points would be. So yeah, it would go like this. Okay, and then from pi over 3 to pi over 2, R is still negative. That would complete this petal. And then from pi over 2 to 2 pi over 3, okay, R would be positive again. And at 2 pi over 3, R is 1, 2, 3, 4. So it'll go like so. Okay, and then between 2 pi over 3 and 5 pi over 6, positive, positive, positive. Okay, and then between pi over 6 and pi, R is negative. And notice that at pi, R is equal to -4, so that's going to actually take us back to close that petal. And we are done. Okay, and you can go ahead and use your calculator and check out these graphs. See if you can come up with some ideas for like how many petals each of these equations, each of these rose curves would have. Okay, and after you do the exploration, you can check out the rose curves summary. So graphs involving cosine will have polar axis symmetry. Graphs involving sine will have symmetry about the line theta equals to pi over 2. Now, if n is even, Then the rose curve has 2 n petals, so you can multiply n by 2. So like if n is 2, there will be 4 petals that have a length of a, and traced out between 0 and 2 pi. And if n is odd, then the rose curve will have n petals with a length of a and traced out between 0 and pi. So those are things you can kind of memorize. Okay, and then the last curve that we're going to talk about is going to be not rose curves, lemniscates. Lemniscates are kind of interesting, and I'm probably saying them incorrectly, but they end up looking like infinity symbols to me. So first of all, this equation is kind of different than what we've been looking at, right? R squared. So that means that R can be positive or negative. Okay. So for graphing, like we have to think about this in a little bit different way. Like I'm not going to I don't know how to graph the square root of 16 cosine 2 theta, but I do know how to graph what's underneath there. We can use that with helping us determine what R is. So I'm going to think about graphing y equals to 16 times cosine of 2x. So that means period would be pi, so we'll go by pi over 4s. Oops, pi. Sorry you guys, I'm skipping angles here. Getting a little tired. Two pi. There we go. 16 negative 16. Okay, and we're talking about cosine here. Okay, and then I'm going to make a table here with a few columns. So theta, okay, and then that would end up representing like 16 cosine 2 theta ends up representing r squared, right? So come up with r squared just from referencing the graph and then the values of r. So going through here, like 0, we would have 16, so r would be 4. Sorry, plus or minus 4. So that ends up graphing 2 points, right? So 1, 2, 3, 4 when r is 4, 1, 2, 3, 4 when r is negative 4. Okay, I'll switch to using just blue here. So for pi over 4, r would be 0. R squared would be 0, so r would be 0. Okay. Pi over 2, r squared would be negative 16. Well, if r squared is equal to negative 16, r would be undefined. Okay, so that corresponds to, use red here. So that corresponds to wherever the graph dips below the x-axis is going to give us values that are undefined because it would make r squared negative. So we can kind of ignore those values here. You could almost think about blocking them off on your polar coordinate system. But then referencing the graph, like back at 3 pi over 4, we're back to 0. And then if we go to pi, we're up at 16 again, so we have plus or minus 4. So what ends up happening is the graph goes from 0 to pi over 4 is positive, positive, positive. And it's blocked out from pi over 4, like no points are plotted. If you think about it like as kind of like going around a clock, if you think about starting at 0 and then rotating the counterclockwise direction, between pi over 4 and 3 pi over 4, there's no points being plotted. But then from 3 pi over 4 to 5 pi over 4, okay, those are positive values of r again, or of r squared. Yeah, so positive, but they're also negative. So positive values of r squared. I apologize, I can't talk. Positive values of r squared repeat, but also that means that we would have plus or minus values, positive and negative values for r. So like between 3 pi over 4, you would have positive values and negative values being graphed at the same time. So like here and here. I guess I kind of missed that on the, sorry about that. We would have had positive and negative values going from 0 to pi over 4 as well. This is one that we can talk about graphing on the graphing calculator and watching like in what order the points are graphed too, and it's interesting. And then I'm going to leave this one for us to talk about in class for finding a point of intersection of polar curves.